Good day, students. As you all know that the line in an XY plane can be worked out if its point as well as the slope or the direction are given. The same applies when we in three-dimensional spaces or R3, where we can work out an equation of a line when we know the point P0 given as x0, y0, z0, and the direction. So if we know the point and the direction, we can also work out an equation of a line in three-dimensional space. By vector addition, we have that R is equals to R0 plus A. These are in bold just to indicate to you that they are vectors. If we go back from previous lecture, you know that in order to add two vectors geometrically, the sum of them will be the diagonal of a parallelogram or the line that completes the triangle. Clearly here, R is just equals to R0 plus A, as it is given in this equation here. A and V are parallel, which implies that A is some multiple, which implies that V is some multiple of A, or A is some multiple of V, because the vectors are parallel. So in other words, you can say that A is equals to TV because the two vectors A and V are parallel. Hence, R is equals to R0 plus TV, because A is TV, we just replace A with TV, which is a vector equation of a line. So a vector equation of a line is given as this equation here. Okay, we already shown that by vector addition we have that R is equals to R0 plus A, right? Which can also be written as R is equals to R0 plus TV. So since these are vectors and we are in R3, this equation can be written in a vector form as x, y, z, right? x0 plus ta, y0 plus tb, z0 plus tc. Obviously, if we in R3, R0 is in R3, V is in R3, T is just some scalar multiple of it. So when we add two vectors that are in R3, we end up with a vector in R3 as in here. So this is the vector form of an equation. As we go on, you will see that sometimes I will give you an initial point as well as the direction and ask you to find the vector form of an equation. And this is what I would like to see. V is the vector that gives the direction in T, right? V is TV, or the direction vector. And V is made up of A, B, C, right? V is a vector and is in R3, which means it must have three components, which are A, B, and C, right? And TV is just a multiple of it, which is TA, TB, and TC. So the equations below are called parametric equations, right? Obviously, the x component is given as x0 plus TA, right? The y component is given as y is equals to y0 plus tb, and the z component is given as z0 plus tc. Here's an example, example 1. We need to find a vector equation, right, and parametric equations for the lines that passes through the point 513 and is parallel to the vector I plus 4j minus 2k. So since our point is parallel to this vector I plus 4j minus 2k, I plus 4j minus 2k is going to be our direction vector. So R0 is just the same as, if we write it in terms of I, j, and k, R0 is 5i plus j plus 3k, right? And as you all know, the vector equation is given as r. R is equals to r naught plus tv, where v is the direction vector and t is the actual direction. So obviously r naught is given as this, the direction vector is given as this vector over here. If we group together I, j, and k's, we get 5 plus ti plus 1 plus 4tj plus 3 minus 2tk, which is the vector equation. So we already found the vector equation. The parametric equation is simply the first component, or the x component, which is x is equals to 5 plus t, and the second component, which is also known as the y component, we can say y is equals to 1 plus 4t, and the third component, that is your z component, is just 3 minus 2t. So we found our vector equation. Now in this equation, in number 2, they say find 2 points on the line where t is equals to 1 and t is equals to -1. In this case, we are given the value of t. Once we are given the value of t, we can just substitute it into our vector equation or parametric equation. When t is equals to 1, we have that the first point will be 6, right? 5 and 1, right? You just substitute into this equation. And when t is equals to -1, x is 4, right? Y is -3, and z is positive 5. Excuse me. So we already discussed vector equations as well as parametric equations, but there's another representation of an equation which is known as symmetric equation. Once we have the vector equation or the parametric equations, it's very easy to work out the symmetric equation, right? What we have here is the parametric equation. We can easily change it into a symmetric equation by solving every component in terms of t. For instance, TA for the first component is just x minus x naught when we take x naught to the other side, which implies that when we solve this in terms of t, we have that t is x minus naught over a. We do the same for y. We solve this y equations in terms of t. We get that t is equals to y minus y naught over b. We solve the third component in terms of t. We get that t is equals to z minus z naught over c. Obviously, all these equations here are equals to t, right? If all of them are equal to t, it means that they equal to each other because all of them equate to t. So the symmetric equation will be that x minus x naught over a is equals to y minus y naught over b, and which is in turn equals to z minus z naught over c. So these equations here are the equations here are known as symmetric equations. So that's how you would be able to move from parametric equation or vector equation to symmetric equations. Okay, so we have more on line segments, right? At this stage, we know that the equation of a line can be given as r is equals to r naught plus tv on r3. So if our line also passes through r1, then we take the direction as r1 minus r naught, right? And the vector equation can be written as r is equals to r naught plus t R1 minus R0. If we manipulate it further, we have that R is equals to 1 minus T times R0 plus T R1. So if the parameter T is between 0 and 1, we know that we are on the line segment. If you draw a line here and T is between 0 and 1, you know that you will always move on the on a point that is on a line. You won't go above the line or below it. We have more examples here just to clarify the concepts that we have just discussed. So we have we need to find a parametric equations as well as symmetric equation of a line that passes through A and B, right? So what we need to do is to find the direction. The vector A is parallel to this line here, so we get AB, which is the same as 3 minus 2, negative 1 minus 4, and 1 minus 3. So the difference or the direction vector will be 1 minus 5 and 4. Remember, when we need to find parametric equation of a line that passes through 2 points, the direction vector, we can get the direction vector by subtracting the final point from the initial one, which is what we have. If I can just go back, which is just the same as this. We take the direction as R1 minus R0 if our line passes through 2 points R1 and R2 and R0. So we get the direction vector, which is 1 minus 5 and 4, as I've already indicated in this point here, right? So we have that our direction vector is this one, and our initial point is A, which is 2, 4, and negative 3, which means that our parametric equation for the x component will be 2 plus t, because A is 1. Remember, the equation of a line is given as R is equals to R0 plus TV, where V is the direction vector. So all our direction vectors will be, components will be a multiple of t. So the first component is just 2 plus t. The second one is just 4 minus 5t. And the third one is negative 3 plus 4t. So the symmetric equations, obviously we find them by simply solving every component for t, are given as x minus 2, which is equals to y minus 4 over negative 5, and the z, which is just simply z plus 3 over 4. So these are my symmetric equations. All of them are in terms of t, they equal to t, which means they equal to each other, right? And in number 2, we want to know the point that, at what point does the line intersect the xy plane? We all know that as soon as our line intersects the xy plane, it means that the z component is 0. So we're just going to substitute 0 into this equation to find that x minus 2 over 1 is equals to y minus 4 over minus 5 is equals to 3 over 4, because z is 0. If we solve for x and y for this in this equation, if we solve for x and y, we get that x is 11 over 4 and y is 1 over 4. So the line intersects the xy plane at 11 over 4, 1 over 4, and 0. Okay, we have another example here. We are given 2 lines in R3, which is L1 and L2, right, with together with the parametric equations. In this here, we need to find out if these lines are either parallel. If they're not parallel, we need to find out if they intersect. And if they are not parallel and do not intersect, we can say that the line are skew to each other. So we need to find out if they parallel. So if we look at all the direction vector of all these lines, right? The first line, we have that the direction vector will be 1, 3, and -1. And the direction vector for the first, remember that direction vectors are multiples of parameters. So here our parameter is S, right? So the direction vector for the second line is just 2, 1, and 4. So since these lines are not, these points, clearly they're not multiples of each other, right? If they're not multiples of each other, it simply means that these lines are not parallel. So we can conclude that line 1 and line 2 are not parallel, right? Now in order to find out if these lines are, if these lines intersect, right, we need to find the values of T and S such that these lines are all equal, such that 2x is equals to 1 plus t, 3x is equals to 3 plus s is equals to -2 plus 3t, and -3 plus 4s is equals to 4 minus t. So what we need to find out is the unique value of t and s such that every component of these lines, of these two lines, is equal. So what we need to do is to solve for s and t, right? So we can solve for s and t. For instance, by the first equation, if we use this, if we use this equation here, 2s is equals to 1 plus t, we have that t is equals to 2s minus 1, right? So we can take these two equations. We have two equations in, we have two unknowns in two equations, which means we can uniquely solve for s and t without even having a look at the third equation. So that's what we're doing here, right? So when you work these out, you can even take the last two equations. It's fine with me. The point is, as long as you can find t and s such that every component of these vectors is equal to one another. That's what you need to arrive at. Even if you choose two equations that are different from mine, you will still get the right answer. So what we have here, we substitute the first equation, this one here, into the second equation. So the second equation is 3 plus s is equals to -2 plus 3t. 3t is just 2s minus 1. So we solve these equations to get -2 plus 6s minus 3, which is equals to -5 plus 6s, right? But you still keep in mind that 3 plus s is equals to -5 plus 6s, right? We take, we get 5s, we take this s to the other side, right? Which means that s is equals to 8 over 5. We already know that t is equals to 2s minus 1, but now s is 8 over 5. We substitute to get that t is equals to 11 over 5. So what we do now, because we found these values of t and s, we substitute them back into these equations here, right? We substitute them, t here, which is 11 over 5, right? And we substitute s here, which is, we substitute t here, which is 11 over 5, and s here, which is 8 over 5, right? So we check if these values satisfy the third equation. Clearly they will satisfy the first equation and the second equation, but we need to find out if the third equation will be satisfied. So negative 3 plus 8 over 5 is negative 5 over 5. 4 minus t is 9 over 5. So the third component is violated. Negative 7 over 5 is clearly not equals to 9 over 5. So these lines do not intersect, right? Because we cannot find a unique value of t and s such that all the components of our lines, all the components are equal, right? So we cannot find such values. So they do not, such value for s and t do not exist. So they're not equal, or they do not intersect. We also said that they are not parallel. So if that's not the case, we say that these lines are skew. So we have class exercises here. Normally, we do these together on a board, but I've prepared solutions, so we will go through the solutions that I've prepared. So we need to find the parametric representation of a point 42 in the direction 1, 1, right? I'm sure you, so what we need to find is r is equals to r naught plus tv. We have an initial point and the direction vector. So let's see. Right, we're in R2. So r is equals to r naught plus tv. The initial point was 42, which is 42 here, and t was, the direction was 1, 1, right? So the parametric equation, this is for the x component, is just x is equals to 4 plus t, and the y component is just 2 plus t, right? So in this case we are in R2. In this case we are in R2. If we were in R3, we would have had the third component, which is the z component. And then we need to find the non-parametric representation of an equation. X1 is equals to 4 minus 2t, and x2 is equals to 3 plus 6t. So here we are still in R2. We have the first component is given as this, and the second component is given as that equation. So the non-parametric representation is simply the representation that you used to, which is the representation y is equals to mx plus c, which is the equation of a line as you know it from high school. So what we do here is, what I'm doing is I'm solving the first equation. The first equation is x1 minus 4 is equals to 2t. I solve this for t, right? So t is equals to negative x1 over 2 plus 2. And once I have solved this equation for t, right? Once I solve the first component for t, I need to substitute this t into the second component, which means, if you recall, x2 was 3 plus 6t. Now I have x2 is equals to 3 plus 6t. Remember, 6t was given as negative x1 over 2. My text got cut here, plus 2. So I simply need to multiply out the brackets. I have 3 minus 3x1 plus 12, which is negative 3x1 plus 15. So clearly this is in the form y is equals to mx plus c. In this case, remember, normally in high school when we were in R2, we will just say xy, just to show that we're in R2. But as the mathematics advances, we use x1, x2, x3, x4, x5, because sometimes we can deal with 5-dimensional space or n-dimensional space. So if you just use the alphabets, at some point you will run out of the alphabets. So in order to be more general, we normally say x1, x2, but x2 is just the same as y, your y component, and x1 is simply your x component. So we use subscripts so that we do not run out of alphabets. So if I just to show you in a way that you're familiar with, we have that y is equals to negative 3x plus 15. This equation here is of the form y is equals to mx plus c. So that's how you get from parametric representation to non-parametric representation. So we need to go back to solve the third exercise. So in the third exercise, we need to find the parametric representation of 2x2 is equals to 3x1 plus 5, and x2 is equals to negative x1 plus 7. Obviously, in number 1 and 2, you can see that these equations are in the form that you used to, like y is equals to mx plus c. For instance, in number 1, if you divide by 2, you will get that your gradient is 2 over 2 and your y-intercept is 5 over 2. So clearly, these are not in parametric form. They are in non-parametric form. So let's see how to do that. Okay, the reason why we say it's parametric equation is because our equations, our components, x and y, are in terms of a parameter t, hence the name parametric representation. So in this case, we just let x1 be t, right? If x1 is t, it means that 2x2 is equals to 3t plus 5. It means now we can solve for x2 in terms of t. So we divide by 2 to get that x2 is 3 over 2t plus 5 over 2, right? So this is the first parametric representation, and this is parametric representation for the first component, and this is the parametric representation for the second component. So once we have this in parametric equations, I'm happy. But if you want to go on to write it in a vector form, it's just the same as x1, x2. Remember, we're in R2. x1, x2 is equals to, for all our t, right? For the first equation, we have that this is 1, but in the first equation, we don't have the intercept, so we simply add 0, right? So x1 is just the same as t, right? And in the second component, our t is a multiple of 3 over 2, so we have 3 over 2 as the second component of the vector. And the y-intercept in this case is not 0, it's 5 over 2. So the vector representation will be of this form, right? So this is the vector representation. These one where x1 is t and x2 is 3 over 2 plus 5 over 2 are known as parametric representation. And this is the vector form of the equation. And 3.2, the same analogy just carries on, right? We let x1 be t, right? Once x1 is t, we solve for x2 in terms of t, which will be x2 minus t plus 7. So this is clearly our parametric representation. But we can move from parametric representation to the vector form of an equation, which will just be x1 is equals to 1. It's just 1 times t but x1 has no y-intercept, which means, it has no y-intercept, which means that we will just have 0. And x2 is -1 times t, which means we will have -1 and 7, because here the intercept is non-zero, so we add 7. So this is the vector form of an equation. So we need to move on to number 4. In number 4, we need to find the parametric equation of the line that passes through 3 naught, right, and 5 naught, as well as the midpoint of the line P1, P2, right? So what we're doing here, obviously our line passes through 2 points, so the direction vector will just be the vector P2, P1, P1, P2, which is simply 5 minus 3, right? 5 minus 3 and 0 minus 0. So we get 2 and 0. That will be our direction vector. And the initial point is 3 and 0. So this will be, we have 2 naught from 5 minus 3 is 2. 0 minus 0 is 0. So the vector equation will just be 3 plus 2t, right? And the second component of this vector is just 0. We have 0, 0. So this is, we found the direction vector 2 naught, 2, 0, right? And then the midpoint of this line P1, P2 will just be 3 plus 5 over 2, right? And 0 plus 0 over 2, which will just be 0. I don't know if you still remember how to find the midpoint, which will be your the x1 plus x2, right, over 2, and y1 plus y2 over 2. That's what we did. So we get 4 over 0, which is the midpoint of 2 points. And then we have another exercise. In this exercise here, we need to find out if this point 11, 14, 17, 18, if it lies on the line 1, 2, 3, 4 plus t 5, 6, 7, 8. Clearly here we in R4 because we have 4 components, 1, 2, 3, 4. So we need to check if this point lie here. This point will lie on the this point will lie on the line if and only if there is some value, if we can find a value t, such that when we add these two vectors here, we get 11, 14, 17, 18. So we need to find the unique value of t that satisfies our equation. How we do that, I have a very clear detailed solution here. So we must have that equation and solve for t. For the first equation, we have that 11 is equals to 1 plus 5t, and we solve t to be 2, right? Since t is 2, we want a unique value of t, which is 2 here. So we substitute. The first component is 1 plus 10, which is 11. We happy. It is equals to this component here. 2 plus 12 is 14. We happy. 3 plus 14 is 17. We happy. But 4 plus 16 is 20, which is not equals to 18. So there is no value of, there's no unique value of t that satisfies this equation here. So we can say that the point does not lie on the line because we cannot find a unique value of t. And then we move on to number 6. In number 6, we need to find the line through the point 6 minus 5, 2, and parallel to the vector 1, 3, negative 2, and 2 over 3. And in number 7, we need to find the line through the points negative 8, 1, 4, and 3, negative 2, and 4. So all of these questions are straightforward, and we can use the concepts that we have already covered. So we are given that we were given the initial point as well as the direction vector. So the parametric equation is 6 plus t, negative 5 plus 3 over plus 3t, and z is equals to 2 minus 2 over 3t, right? So in this equation, in number 7, what we needed to do is to find the line, the equation of a line that passes through A and B, right? So the direction vector is AB, which is the final point minus the initial. So we have that 3 minus 8 is 3 plus 8, negative 2 minus 1 is negative 3, 4 minus 4 is just 0. So this is the direction vector, and the initial point is negative 8, 1, 4. So the vector equation is given as negative 8, 1, 4 plus t, and the direction vector is 11, negative 3, and 0. So the parametric representation will just be x, negative 8 plus 11t, that's the x component. The y component is 1 minus 3t, and the z component is simply 4, because the direction vector takes the value 0 in the third component. Okay, up to this point, we covered equations of a line in R3 and R2, right? So we move over to planes. So a plane is just it's like a sheet in space, right? The way we drew planes in previous exercises, right? So as we know that with regards to lines, in order to find an equation of a line, you need a point and a direction. But then with regards to planes, we in order to find the equation of a plane, you need to find its norm, right? So a line parallel to the plane does not specify its direction, but a vector perpendicular to the plane is more helpful, which is a norm, right? So we can only find the direction by means of a norm, not a line that is parallel to a plane. So a plane in space is determined by its initial point P naught and a vector n called a normal. So you must always know that a normal is a line that is perpendicular to your plane, right? So this is what we have here. We have this sheet here. It's a plane in R3, right? And then we have our vectors from the origin R and R naught, right? And then R minus R naught is this line here. So when we say R minus R naught, we are still on the plane, right? But then a norm is this red line here, which is clearly perpendicular to R minus R naught, hence it's perpendicular to the entire plane. So that's our normal vector. It's perpendicular to R minus R naught, which makes it automatically perpendicular to the plane, because R minus R naught is a line that lies on the plane. So the vector r minus r naught is represented by this displacement here, p naught p, right? R minus r naught, this vector, it's p naught p, right? The vector n is orthogonal or perpendicular to every given vector on a plane, which is true. This line here is perpendicular to r as well, the norm. If we were to take the line that's parallel to the norm, is this line here. It is perpendicular to r. Remember, all the lines that are parallel to the norm will also be perpendicular to the plane. So if I have a norm here, this norm is perpendicular to r naught. It's also perpendicular to r minus r naught, and it's also perpendicular to r. If we were to move it just here, you will see that a norm is perpendicular to every line that's on a plane. So we say the vector n is perpendicular to every given vector on a plane. Hence, n dot r minus r naught, because r minus r naught is on a plane, is equals to 0. So the above equation is called the vector equation of a plane. So in order to obtain the scalar equation, obviously this is a dot product. We dot together two vectors in R3, 1, 2, 3, we will get a scalar. So r minus r naught, as you can see that it's a scalar, but as you recall, r is just the point x, y, z. If we go, see, r is a line from the origin, and the point here is x, y, z, whereas r naught is also a point from the origin with its coordinates being x naught, y naught, and z naught. So what we're doing, r minus r naught is simply x minus x naught, y minus y naught, z minus z naught, which is what we have here. And our norm, the coordinates of our norm is just a, b, and c. As you can see, it's just that it's not given here, but the coordinates of the norm will just be a, b, c, right? We dot this together, we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equals to 0, right? Which is a scalar. That is why we say the vector equation of a plane can be given by a scalar equation. This is the scalar equation. So the above is known as the scalar equation of the plane through the point P naught with the normal vector given as n, where n is ABC. We have an example which will make the concept even much clearer. We need to find the equation of the plane through the point 2, 4, minus 1 with the normal vector n, which is equals to 2, 3, 4. Find the intercepts and sketch the plane. Okay, so our normal vector is ABC, right? The first component 2, the second being 3, and the third being 4. And our initial vector is P naught, x naught, y naught, z naught, which is x naught is 2, y naught is 4, z naught is -1, right? So when we apply our formula, A is x minus x naught plus by minus y naught plus c z minus z naught is equals to 0. We can easily find the equation of the plane by direct substitution. So A is 2, right? X is just an arbitrary point. We don't know what it is. We have 2x minus 2 plus 3y minus 4 plus 4 times z plus 1 is equals to 0. We multiply out the brackets, right? And add common factors, we arrive at this equation. So the equation of the plane is 2x plus 3y plus 4z is equals to 2, right? And the other way of writing this equation is to take the constant to the other side, where we simply have ax plus by plus cz plus d is equals to 0. So this is just a linear equation in x, y, and z. We say it's linear in a sense that our variables do not have squares in them. It's not quadratic, right? It's not a cubic equation. It's not raised to any powers. So that's why we're saying it's a linear equation in R3. So we also need, we have another example here when we need to find the equation of the plane that passes through the point P 132, Q3 minus 1, 6, and R520, right? So we need to find the equation of a plane that passes through these 3 points here, right? So in order to find the equation of a plane, we need to find, as we have already said, that in order to find the equation of a plane, first of all, you need to find the norm, right? The norm is the line that is perpendicular to a plane, or every single line that lies on the plane. So PQ, right? If we have a plane PQR, which will look like a triangle, a sheet of a triangle on R3. So any point that is perpendicular to that plane should be perpendicular to the vector PQ and PR. That's why we need to find the vector PQ and PR. So PQ will be 2, -4, and 4, right? Which is 3 minus 1, minus 1 minus 3, 6 minus 2. Right, and PR is also the same as 5 minus 1, 2 minus 3, and 0 minus 2. 0 minus 2. So PR is this one here, right? So we need to find a vector that is perpendicular to both A and B, right? If such a vector is perpendicular to A and B, or this displacement PQ and PR, we show that such vector will also be perpendicular to PQR, right? Because it's perpendicular to these line segments. So both A and B lie on the plane, right? If both A and B lie on a plane, it means that the vector that is perpendicular to this line, to A and B, is a cross product of them. A cross B will be perpendicular to the plane. So as you already know from the previous lecture, that this is the idea we need to apply in order to find the cross product of two vectors. We start with our vectors that we found, 2 minus 4 and 4, 4 minus 1 and -2. We find the cross product, and the cross product will be 12i plus 20j plus 14k. At this point, I take it for granted that you know how to find a cross product. I'm not going to go into too much details. So obviously our cross product is a norm, right? Which is 12, 20, 14. And our initial point is P, which is 1, 3, 2. So the equation of the plane, as you already know by definition, will be 12x minus 1 plus 20y minus 3 plus 14 times z minus 2. And then we'll multiply everything out, right, to get this. This should be 50 because I multiplied out the brackets, right, and added up the common factors to get 100. And after that, I divided this by 2, right? 6, 10, and 7. And 100 divided by 2 is 50. So this should be 50. can just take note of that. So this is the equation of a plane that passes through the point P, Q, and R. Okay, let me just go back. Okay, here we have test yourself exercises. You know, we normally do these exercises in class, right? Or I ask you to attempt them independently and then I give you solutions afterwards. But since this we're not in class, I already have the solutions for all of these questions, so I will go through them with you. So given the work that we have already covered so far, you can actually attempt exercise 10.32 to 10.41 in your textbook, which is Mathematics for Economists textbook by Simon and Bloom. So those exercises, you should find them from Simon and Bloom. So we need to find the symmetric equations of 2.1 and 2.2, right? I mean, I've gone into into details in terms of how you find symmetric equations, and we have done examples on that. So what you can do is this, it's 2.1, right? Just ignore the solution here. It's not supposed to be here because we're busy with 2.1. So 2.1 you can do, what you need to do is just to solve x1, x2, x3 in terms of t and equate them, right? The same applies, the same idea applies for 2.2. So you can do 2.2 as an exercise. I already have the solution for 2.1 here. As you can see, I solved for the first component. I solved this first component for t. I also solved the second component for t and the third one. Once I've solved these for t, I equate them together, right? And if we move on to 3, find the equation of the plane through a point 1, 2, 3, normal to the vector 1 and negative 1 and 0. In this case, it's much easier because we are given the normal or the norm, which is 1, negative 1 and 0. So what you simply need to do is, we know that the equation of a norm is n dot r minus r naught is equals to 0, right? Where r is x, y, z, is arbitrary, and r naught is a given point. So our norm here is 1, negative 1 and 0. We subtract r from r naught to get x minus 1, y minus 2, z minus 3. This is the dot product. We multiply everything out. 1 times x minus 1 is x minus 1. Negative 1 times y minus 2 is just minus y minus 2 plus 0. We simplify further. We get that the equation of the norm is x minus y is equals to negative 1. So we need to, for number 4, we need to find the equation of the plane that cuts through a point 1, 1, negative 1, and perpendicular to the line, right? This is the equation of a line. X, y, z, 4 minus 3t, 2 plus t, plus 6, 5t, right? So what we have here is that our plane passes through and it's perpendicular to this line here, right? So if this if our plane is perpendicular to this line, it means that it should be perpendicular to the direction of this line, because this line is in the direction -3, 1, 5. So automatically in this case, our norm will be -3, 1, and 5, right? And then we're going to apply the equation of a norm, which will be -3, 1, 5 dot x minus 1, our given point, y minus 1, z plus 1. We simplify further, we get that the equation of the plane is -3x plus y plus 5z is equals to -7. So we need to go back to number 5 to see the description of the question. Use Gaussian elimination to find the equation of the line, which is the intersection of the planes x plus y minus z is equals to 4 and x plus 2y plus z is equals to 3. So clearly, if we need to find the intersection, it means we have to equate these equations and solve for x, y, z. But if the other way of solving for x, y, z is simply to use Gaussian elimination, which is what we're going to do because that's what the question requires, right? So if I use Gaussian elimination, I take the coefficients of the first equation, right, to form this augmented matrix here. I get my equation into into echelon form, right? Once this is in echelon form, I cannot reduce it any further, where my pivots are 1 and 1. As you can see, z is the free variable, right? It's not a pivot. So since z is a free variable, we can let it be anything because it's free. Now suppose z is t. When z is t, we have that y is equals to -1 minus 2t, right? But x plus y minus z is equals to 4, as in the first row here. We know that y, we solved it in terms of t is -1 minus 2t, and z is also t minus t is equals to 4. So we have this equation here. We can solve for x in terms of t, which is x is equals to 3t plus 3, right? And then we have x, y, z. Obviously, what we have is a parametric equation. We can have it in a vector form. So what we have is x, y, z. X is 3t plus 3. It's 3 plus 3. Y was -2t minus 1, which is -2. Some multiple of t minus 1. We let z equals to t. It was simply t. So the coefficient is just 1. It had no y-intercept. So this will just be 0. So that's the line of the equation. It's the line of an equation where two planes intersect. The last equation, the last question, you can just read through the solution by yourself because it's very much similar to what we covered in previous slides. For instance, we need to derive a parametric and non-parametric equations for the lines that pass through the pair 1, 2, and 3, 6 in R2. Okay, if our lines cuts through these 2 points, obviously you need to, in order to find the direction vector, you need to subtract the initial point from the terminal point. which is what I did here. So these will be, I subtract the initial point from the terminal 1 to get 2, 4, which will be my direction vector, 2, 4, t. My initial vector r0, which is 1 and 2. I solve for these parametrically. This is the vector equation, and the parametric equation is x is equals to 1 plus 2t, and the second component is y is equals to 2 plus 4t. And then we're done with the solution. So all of these concepts that we have covered do have economic implications. So normally it's better to deal with the maths in its purest sense. Once you understand the mathematics, then it becomes very easy to understand the application. So when we were busy with the lecture, I did point out to the fact that we don't use, for R2, we don't use XY anymore as you did in high school. We normally say X1, X2, because as the mathematics gets more advanced, we deal with higher dimensional spaces, right? For instance, on your commodity space, right? If we have a commodity space or goods space, you consume more than 2 products, right? There's so much that you consume. For instance, our vector x will be the commodity space made up of x1, x2, x3, x all the way to xn, because we don't live in a two-good world, right? Where xi is greater or equals to 0 for all I, because in economics, we don't consume on negative space, right? You cannot eat negative 2 apples, negative 1 banana. That does not apply. So our consumption space is in the positive quadrant, right? I mean orthant, because we're dealing with higher dimensions. So the commodity space lie on the positive orthant of Rn, right? That's why we don't say XYZ, but in this case we did use alphabet XYZ because we were in 3-dimensional space. But if we move on to higher spaces, we just use X1, X2, X3 all the way to Xn, right? And then we also have the price, right? If Pi greater than 0, obviously the price will also be greater than 0. Denote a price of commodity I. Then the cost of purchasing commodity bundle. If you're fortunate enough to consume everything on the n-dimensional space, right? It means your budget should be way higher. So we have that P1x1 plus P2x2 plus P3x3 all the way plus Pn xn is just P dot x, which is boldface, which means here we have P1, P2, P3 all the way to Pn dot x1, x2, x3, xn all the way to xn, and then we get the dot product, which is this one here. We have already done a dot product when we were finding the equation of a plane in R3, right? So a consumer with budget I can only purchase bundle X such that Px is smaller or equals to I. This is your budget set, and it is bounded above by the hyperplane P dot X is equals to I. Previously, the equation of a plane, right? In order to find the equation of a plane, you need its norm, right? Here our norm is P. You need its norm and its initial point, E with its initial point. So you dot the norm with X minus the initial point. Here we don't have the initial point, so we simply dot it with X is equals to I. So in R3, the equation that we found is a plane. In R2 you have a line. In R3 you have a plane, right? But as the dimension gets larger, like when we are in n-dimensional plane, this is no longer a plane, it becomes a hyperplane because you are simply in higher dimensional spaces. So this equation of your hyperplane px is equal to I is simply the same as the equation of a norm that we found earlier. It's just that with a norm we were dealing with we were on R3, or we were in 3 good space. And then these ideas can also be applied to our investment models in portfolio theory, right? Where you can consume n tuple assets or n tuple shares. Obviously, with regards to shares, your shares will have prices as well, right? And then you can buy so much quantity of ShopRite, given that the price of a ShopRite share is maybe 126, right? So depending on your budget, if the price is given as 126, if you want 10 shares of ShopRite, your budget should be 1,260. So that will be your price dot the quantity of your assets, which is smaller or equals to your budget. So that will be your hyperplane of what you can consume in that n space. Okay, we also go on to for instance, with ISLM model, you have that the parallel hyperplane also applied to your ISLM model, where shifting of output results into a hyperplane that is parallel to the original one. Obviously, when you want to move on to, when you shift a model, it means that you're just going up, right, above the initial line, which is just, that will just be a line that is parallel to the initial one. So in order to, for more details on these applications, you can see Simon and Bloom, page 233 to page 236. Thank you very much for listening. Okay, before going on any further, I just want to go through the summary. I'm sorry about that. I just need to go through the summary so that you know where to focus on when you study for this course. Okay, you should be in position to illustrate lines and regions in R3, which I think is something that we did with regards to the tutorial worksheet that I have posted. Right, you need to project, the student should be in position to project points from R3 to R2. You need to be able to find equations of a line, of a sphere. And it's important to know how to compute unit vectors, dot products, as well as cross product. And you should know what it means for a vector to be in R. A vector in R is simply a scalar. A vector in R2 will just be a vector with 2 components. A vector in R3 is a vector with 3 components, right? The one in Rn, it will have n components. So you need to give, you need to move from non-parametric representation of equations to parametric equations, or move from parametric representations to non-parametric representation, right? And this is very important. You must be in position to determine or work out an equation of a plane, and you must also be in position to give symmetric representation of equations, and link whatever we have done to the concept of budget sets as well as the investment sets. Thank you very much for listening.